Hi, my name is Madeline Murchland, and I'm an undergraduate at Miami University. This is a mineralogical characterization of Hicks Dome intrusive core samples and related fluorite mineralization in southern Illinois. This project was done with the help of Mackenzie Rutherford and Dr. John Rakovan, who are also at Miami, as well as Jared Freiburg, who is with the Illinois Geological Survey. So the setting for this project is a Mississippi Valley type deposit, or an MVT. MVTs are lead zinc ore deposits. They're low temperature forming and epigenetic, or forming after, the dolostone or limestone of sedimentary basins. This means that they're stratigraphically controlled and often form large districts around the margins of those basins. Ore and gangue mineralization is from highly saline basinal brines and usually occurs as one of three ways, either as open space filling, solution in collapsed breccias, or as replacement of carbonate host rocks. You see two of those methods in these diagrams here. So at the top is mineral emplacement through veins. These veins are often caused by tectonic activity in the area, and in this case you see it cutting through a limestone and hydrothermal fluids moving up through that area and mineralizing it. And then at the bottom is metasomatic stratiform replacement. That was the replacement of carbonate host rocks. Like I said earlier, MVTs are lead zinc ore deposits. So they host important ore minerals, namely sphalerite and galena, which are mined for their zinc and lead respectively. There's also a variety of gangue phases that are found in MVTs. So calcite, dolomite, quartz, pyrite, marcasite, and barite all commonly mineralize in the deposits along with the ore minerals and are well known to collectors as specimen grade material. You see this in localities like the Sweetwater Mine and a variety of Illinois places that produce really nice calcites and barites. MVTs can be further classified into subtypes based off of the other phases that occur there. So the typical Mississippi Valley type deposit is almost or totally devoid of fluorine, but there is a subtype of deposit where there is such significant fluorite mineralization that it becomes an ore phase. The origin of fluorine in these systems, as well as the mechanism that fluorite precipitates from the hydrothermal fluids from, is debated for both of those topics and probably varies based off of the individual deposit. So examples are in the Rio Grande Rift Valley, which includes the famous Hansenburg mining district, that's the largest MVT deposit in the area, as well as the North Pennines ore field in England. So on the left you have a fluorite from the Rogerley mine, which is in the North Pennines ore field, and then on the right is a fluorite from Bingham, New Mexico, which is in the Hansenburg mining district. The Illinois-Kentucky Fluorspar Bar district is a third example of the fluoritic subtype. Not only did it produce the majority of the fluorine ore in the U.S. during the 20th century, but it's also really well known by collectors for the incredibly aesthetic fluorite and combination pieces that have come out of the mines there. The IKFD produces a huge variety of fluorite, and that's evidenced on this slide, as all four of these pieces are from the same mining district, Cave and Rock, but they all look very different in color and zonation. So here is a map of the Illinois-Kentucky Fluorspar district. You'll recognize along the southern margin of the basin a lot of the more famous locality names, that is Cave and Rock, Elizabethtown, and Rosiclare. Also in that southern portion of the map, you'll notice a lot of faulting going on. This makes sense because MVTs are the result of large amounts of hydrothermal fluids moving throughout a system, and tectonics is the driving force behind that movement. This is also seen in two of the main methods of mineral emplacement, that being bedding replacement and vein deposits, both of which are present in the IKFD. Another common characteristic of Mississippi Valley type deposits is that they don't occur near or have any contribution from igneous activity. However, the IKFD hosts Hicks Dome. This is a structural and topographic high situated over a calc-alkaline intrusion in the northwestern portion of the district. It's in this red square here. The dome is a crypto-explosive feature that was created by the release of dissolved volatiles in that calc-alkaline magma at depth. Surrounding the dome are numerous mafic and ultramafic dikes, almost in a radial pattern that essentially create a dike swarm. These igneous bodies have all been through at least one episode of brecciation, if not a few more, and then further mineralized by hydrothermal fluids. The area became of interest to researchers when high amounts of rare elements and rare earths were observed, namely beryllium, thorium, niobium, and yttrium. This prompted the Ozark-Mahoning group in the 1970s to drill several cores from the area. Thin sections were then made of these cores for further analysis, and this past year some of those sections were sent to us at Miami for mineralogical characterization. So the cores that we have, or that we have thin sections of, are located here on the map in the red markers. The Hicks Dome assemblage of breccias includes the upper complex breccia, calcite cement breccia, middle complex breccia, host breccia, and footwall breccia, which are set apart by the size, amount, and type of rock fragments, as well as the amount of fluorite mineralization. Out of those 7, the footwall breccia is the most intensely metasomatically altered. Bradbury and Baxter classified these 7 units into one of 3 categories in 1992, either as shatter, vent, or carbonitic on the basis of geometry and mineralogy. While there are nuanced differences in their creation, all 3 types generally originated from that first explosive activity from the calc-alkaline magma at depth. The breccia that we studied is classified as shatter breccia and represents the host and footwall units. These rocks are characterized by a mix of rock fragments and rock flour matrix with variable fluoritization. These are pictures of some of the actual drill cores from about 2,100 feet to 2,500 feet in depth. You can see even at this scale the dark purple fluorite that's filling the space between the angular clasts that are of all different sizes, as well as lithics that have been fluoritized and silicified. One of the sections that we received is from that third core, in fact, which was taken from approximately 2,500 feet in depth. Macroscopically, it has this dusky purple fluorite with gray silicified fragments, as well as a really fine-grained rock flour matrix. This is what it looks like microscopically in plain polarized light. You can see the purple fine-grained fluorite, and there's both a darker purple and a lighter purple towards the right, as well as colorless grains that are mostly made up of carbonates. Here are 4 pictures, all taken in plain polarized light, just to show the difference in fluorite mineralization. So the upper left image has a red or purple fluorite with colorless carbonate grains and abundant opaque minerals. To the right of that, in the lower right image, are the most generally representative of the fluorite that we saw in the sections. That is dark purple, fine-grained, and filling in that space between these carbonate clasts. And finally, the lower right image here is interesting just because it shows this purple-blue fluorite that's rimming a smaller carbonate lithic. So this is one of those carbonate fragments with the left side of the image in cross-polarized light and the right in plain polarized light with a total field of view of 4.45 millimeters. This is what a lot of the fragments that I observed looked like. That is very angular and made up of fine-grained carbonate minerals that stands out against that really dark purple fluorite matrix. There is a variety of different clasts throughout the sections, and the mineralogy of these can help to determine where they originated from and therefore what part of the breccia assemblage you're looking at. On the left is a carbonate lithic, mostly made up of dolomite with some quartz and a few unidentified opaque grains. The right is another sedimentary lithic with a large calcite grain in the center. Interestingly, a lot of the typical MVT mineralization was found in the breccias that we looked at. Optically, phases like sphalerite, galena, pyrite, and barite were all identified, and the last 2 of these are shown here. So on the left is pyrite amongst some dolomite grains, and on the right is a large area of barite. Among those minor phases that could be identified optically, with its characteristic morphology and high relief, is apatite, specifically fluorapatite. This was the only abundant minor phase in the thin sections that is not common to the typical Mississippi Valley type deposit, but it was really ubiquitous throughout all of the thin sections that we observed. So all 5 of these images here are of fluorapatite from different thin sections. Powder X-ray diffraction was also performed on all of the thin sections using a Brooker D advanced powder X-ray diffractometer for the purpose of phase identification and a semi-quantitative analysis of those phases. So first off, that data confirmed what we had already been seeing through the microscope, which is that dolomite, fluorite, quartz, and calcite are the dominant phases. There were also those MVT minerals in this diffractogram that's barite, pyrite, and galena, along with the fluorapatite that I've already discussed. The diffraction data also showed that there was some TiO2 phases, here it's brookite, along with helping us identify the rare earth and rare earth element phases, an example of which is niobium-rich rutile, which is in this diffractogram. I also tried to get some higher resolution data by running scans for a smaller 2 theta range at a longer step time with a smaller step size. This helped a lot with pulling out those minor phases like the fluorapatite peaks, which you'll see here in that kind of hot pink. There's 2 peaks right around 32 2 theta. It also helped with finding the rare element minerals like the niobium-rich rutile, which here is represented in that kind of teal blue color. This second diffractogram is really similar to the first in that it has dolomite and fluorite as being the two major phases, followed by quartz and calcite. There's that typical MBT mineralization seen by barite here, as well as the fluorapatite, which was ubiquitous throughout all of the thin sections that we looked at. However, this particular core had a higher concentration of rare elements and rare earth elements. This is represented by the minor phases bertrandite, which is a beryllium silicate, xenotime, which is yttrium phosphate, and charoite, which is calcium thorium phosphate. I also started Rietveld refinements from the powder data that I collected to try to get a semi-quantitative analysis of the phases that are in the drill cores. So in this particular refinement, you'll notice that around 47.2 theta, there's a major peak not being modeled. This peak is a harmonic of fluorites 111, which happens to be where fluorite cleaves, so that would suggest that there's an element of preferred orientation that's affecting the modeling here. I also utilized cathodoluminescence to try to find some of these minor phases that were showing up in the powder data that weren't as easily identified in the thin sections in plain and cross polarized light. So in the top is an unidentified oxide that is luminescing in dark blue against this really red-orange matrix. That red-orange color is produced by manganese in the carbonates. To the right of that is a really large quartz grain that's luminescing in a brighter blue, again in that red-orange matrix. And then the two pictures below those are of fluorite grains. That green-blue luminescence is presumably due to rare earth element substitution in the fluorite structure. CL was also really useful in identifying the fluorapatite that was in the sections. So those tiny gray grains weren't always easy to pick out of the large amounts of gray quartz and gray carbonate lithics that were making up all of the slides. But you'll see here that they luminesce a really bright blue against that red-orange background, so this made them much easier to identify. Combined, these methods showed that dolomite, fluorite, quartz, and calcite were the major phases in the drill cores. As for the minor phases, there were the typical MBT minerals, galena, sphalerite, barite, and pyrite. There was also fluorapatite, as well as the titanium oxide phases brookite and niobium-rich rutile. Finally, there were the rare element and rare earth phases, bertrandite, xenotime, and monazite group minerals, which were mostly charoite. This general similarity between the breccias and the MBT deposit above them suggests a genetic link between the bodies. The abundant fluorine, rare elements, and rare earth elements found in the breccia mineralization are likely from the calc-alkaline intrusion, and the proximity to the MBT deposit suggests that they share the same source. The intrusion may also have been the source of heat for the hydrothermal fluids that ultimately mineralize the breccias. The overarching goal of this project is to create a mineralogical setting for a larger chlorine isotope study that would try to find the origin of the fluorine in the system. As for my next steps, I hope to get these thin sections carbon coated so that they can be looked at under a scanning electron microscope, because I want to get a better idea of the chemistry in the minerals and to continue identifying minor phases, with fluorocarbonates and rare earth phosphates being of particular interest. Thank you for your time, and I would be happy to answer any questions that you might have.